All right. Hi, everyone. Thanks for coming to this week's UTIG discussion hour. This week, we're going to hear from our own Eric Hiatt. Eric is a second year PhD student. He did his undergrad at UT as well. And today, he's going to talk to us about modeling in the Martian groundwater system. So take it away, Eric.
Hi. Yeah, like I said, I'm Eric Hiatt, and I'm a second year grad student. Co-advised by Dr. Hess out of the department and Dr. Gulick here at UTIG. And I feel fortunate I actually work with Dr. Tim Gallage enough that he's kind of like a third advisor to me. I'd like to thank all three of them. Today, we're going to talk about modeling the dynamical effects of sequential impacts on early Martian groundwater systems. And we're going to look at this and see if we can understand maybe how these sequential impacts may provide a habitable environment over biologically significant time periods. And so NASA's Habitable Worlds program will be the roadmap with which we look at this. The goal of the Habitable Worlds program is to use knowledge of the history of the Earth and the life upon it as a guide for determining the processes, conditions that it can create and maintain habitable environments. And if you look on your left there, they give us this nice little rubric, the things that NASA believes you need for life, or life as we know it. In the lower left-hand corner, you have CHNOPS, which is carbon, hydrogen, nitrogen, oxygen, phosphorus, and sulfur. And they believe that these are the essential ingredients that you need to actually build biotic life. Next, going up, you need water for the aqueous chemistry to put those things together. On the bottom right would be energy. In the middle will be kind of the focus of this talk is time. You need time to put all these things together. And so leveraging that the habitable worlds, the knowledge of the history of the Earth, on Earth, we have basically two inception scenarios that there's two schools of thought, two camps. One on the left will be the wetting drying camp, where you have these flats and you have some type of hydrothermal spring, and you aggregate that CHNOPS, that material in these places by wetting drying cycles, and you have your energy from your hydrothermal systems, and presumably geologic time frames and water would help. On the right-hand side, you have basically hydrothermal vents at mid-ocean ridge spreading centers, and sometimes these people disagree completely as to whether you could have one or the other. Some people think it's like a hybrid of the two, but those are the two inception ideas that we're working with. And so leveraging our terrestrial understanding, we're going to look throughout the solar system and think, where can we get those ingredients that NASA deems as requirements for life? And the problem is on Earth, mid-ocean spreading centers, we're the only planet that we know of that has plate tectonics. And so we look further around and we see these post-impact hydrothermal systems, terrestrial ones on Earth. This is Chicxulub's artist rendition. But associated with all these hydrothermal systems, or all these impact systems, are hydrothermal systems. The IDP 364 cores confirm that. Spectral evidence on Mars confirms that there's hydrothermal systems associated with these impact systems. And we look around the solar system, these impact systems are ubiquitous. This is Oriental crater. It's a beautiful multi-ring basin. You can see this is actually the outer basin. And it formed 3.8 billion years ago, which will be relevant later. And I imagine from the title of the talk, you can tell we're going to Mars. So we look at Mars and we think about it from that CHNOPS, the ingredients, the water, the energy, and the time. And you need to understand a little about Mars so that Mars can be relevant to us. And Mars is basically this planet split in two. There was two time periods on Mars. We look back, and this is the Nowakian to pre-Nowakian time. On the left-hand side, you actually have the Earth eras here. So we're talking about the Hadean. And the Hadean, we don't have much on Earth. And that's because, the plate tectonics has recycled the crust, and you don't have much information left other than the old cratons. But on Mars, that's a large portion of the surface of Mars, frozen in time from 3.7 billion years ago. But something happened to Mars. And so you went from these times where you had valley networks and you had hydrous weathering to where you have rare floods, extremely rare networks, low erosion rates. You also went through a pH shift. At one point you had phyllosilicates being formed, then you get to sulfates and even like iron-bearing minerals. So something switched, but this isn't really the time we're going to look at. So we're going to look more at the time when it actually had water and it had these impacts. And so we'll go back to the Valley Network era. This is the Nowakian Terra. It's the oldest terrain on Mars. And that's about 2,000 kilometers across. The inset, it's only a couple kilometers. But throughout it, you have these fully integrated fluvial systems, Strahler order 6, Strahler order 7. There's just clear evidence of surface fluvial activity. And we have to take a little bit of a step back because there's before all this, there's something called the global dichotomy, and it will actually it'll come to bear throughout this entire talk. And it's likely formed by a oblique impact that sheared the top of the planet off, almost like a baseball. The crust is significantly thinner. You have 5 to 7 kilometer difference in elevation there, and is the absolute oldest feature on Mars. Next, you have Hellas. Hellas is an enormous basin. It's more than 2,000 kilometers across, 7 kilometers deep. I mean, it's so big that they think there's studies that look at whether it's antipodal litharsis, this large igneous complex you can think of as kind of like the Deccan traps times 10. And people think it may have lensed and actually shut down the magnetosphere. It's large. It will be significant in this talk too. But concurrently with Hellas, you have late heavy bombardment going on. And that's active research now too, as to whether you had, a gravitational perturbation in the solar system, like the Nice model or something like that, or if it was just a tailing of the flux rate for these impactors early in the solar system. But it's clearly evident, there's Agire here, Isidis, and Utopia, that you had a large impactor flux rate. I mean, just several times, 250 times is what I've heard some of the people estimate. And you can remember earlier on the last slide, the Oriental crater that came in at 3.8. So this is spread out across the entire solar system. But we talked earlier, this is also concurrent with the time when Mars had water. And so you have these large impactor flux rates. You have a saturated target rock. And the question is, what do these impacts do to a hydrological system? And so we're going to go back to our Earth understanding and try to leverage some of our terrestrial analogs to understand how big of an effect this might be. So we have just a map of the United States here, and then the white dot there would be Chicxulub for scale. And I think we're all familiar with the Chicxulub crater that killed the dinosaurs. It's 200, well, ended the KT. It's 200 kilometers across, just to make it round. Hellas, we talked about earlier on the earlier slide, would be something like that. And you have to think, Hellas is 32 million cubic kilometers of water if you just do a simple math of the diameter and the depth. That's 13 Mediterranean oceans worth of storage space. And so what would happen to the world's, the oceans? What would happen to them? How would they drain into this? How would the Great Lakes react? How would the Floridian aquifer react? I mean, the continental divide is gone. So how would the Earth's hydrological system react to something like this happening? In fact, it's actually a little bit worse than that because Mars is much smaller. And this isn't scaled for, if you scaled this for size, the gravity influence of that bolide would make this hole much larger. But if you just scaled for surface area, Hellas would look something like that. So obviously these are large scale events that are happening, and they're happening all within 100 million years of each other. So we're going to try to quantify that a little bit and see maybe if we can get some intuition on how much of a change this is. And so we're starting here with a little diagram, and we're going to form Hellas in it, but we got to think these are all globally connected systems. And so if you extend out, this would be the putative northern lowlands, that dichotomy boundary you talked about with the oblique impact. These may or may not have filled in with water. There's a Parker et al. Paper from 1989 that mapped out shorelines on this. And so in looking at this problem, we're going to leverage that too. But you can think about forming something like Hellas here and wondering what happens to the water table on that southern highland. And this really becomes a function of how deep this becomes versus where you started relatively, and then just a porosity of your rock, how much water is held in your rock. And then you can estimate the flux it would take to actually fill this. We ignored the lowlands because that actually, the geometry that takes it off back of the envelope calculations. But so you're just gonna have a parameter space of where you think the ocean might have been and your variance in porosity. And if you graph that, you can actually get a change in, so here we got the porosity variance from 0.1 to I think 0.01 or something. This is the drop in head dependent on where you started your ocean at, and we know where this is. And then on this graph would be the change in your global head in kilometers. This is actually just the highland head. It doesn't take into account the amount of water you pull from the ocean. But just conservatively, you're looking at 250, all the way up to 700 meters of change. And it's obviously not going to change all the way down. It's going to have to draw that much material up from the lowlands, but it's quite significant. I mean, it's just obvious that that's going to happen. And it's also simplified because Hellas is somewhat filled in with sediment, and so the hole would have actually been bigger. And so we have these huge, large-scale basins that form the dichotomy boundary, Hellas, Argyre. And they're going to be pulling water just across on a global scale. But divided under that, we're going to have some actual regional scales too. And what we did here is we modeled a permeability field that was homogeneous. And then the gray circles you see there are impact structures that we just put a permeability to, and then you create a heterogeneous permeability field and aggregated it. It's super simple. It comes back to a steady state too. We did not keep these dynamically. And what you can see is you can actually create a pretty complex flow field. Your flow would be going left to right, and then it aggregates on these clusters of craters. This is the stream function calculated. If you think of blue as topographic lines on a map, on this map it's head gradient lines. Left to right is downhill, and then the stream function calculated within each has equal flow. So where lines are bunched together, there is more flow, and spread out, there is less flow. But you can play this game, and we just form something bigger, and this is about, I guess, half the size of the Chicxulub crater, and you can significantly alter the entire flow field of the region. And this is just by creating a topographic low. And like I said before, this is completely gone back to steady state. We didn't model the dynamics. This is just to develop intuition, but there would be a chatter behind all this of those smaller craters forming and not coming to equilibrium. But even more, we can play that game once more and hit it with something bigger, and you can actually reverse regional gradient flow, like up gradient. So even if you had, say, Hellas or the dichotomy on your right, you could have flow going away from Hellas in the dichotomy just regionally while these things come back to equilibrium, just from the topographic low and the accommodation space you create. And here, just for fun, we did a little advective trace to see what it would look like. And interesting enough, I think they aggregate on these little clusters of craters. I think it's interesting. And we talked about the global gradient, and that's the regional gradient. But underneath, that's that little chatter I was talking about. We're going to go ahead and form a secondary crater. So this crater is filling, and then another crater is going to form right here. And you can see this groundwater mound that forms, and they come back to equilibrium. And this can be, let's change it on. This can be like, there's multiple, what we're getting at here is there's multiple gradients nested amongst each other. You have a lot of dynamic movement. You have a lot of ability to move water. But the question is, what are those time scales? Like we're going to keep going back to that. Like what rate do these things fill out? How fast do they fill? And what implications might that have? And so the easiest thing to do is to look at the time scales associated with just one crater. These are completely unconstrained. Does it take 1 million years, 10 million years, 10,000? It's not been looked at yet. And so the first thing we're going to ask, if you want to do this numerically, is what are the appropriate equations we want to use? And then there's multiple ways to do this. Laplace, more than even up here, multi-phase. We choose the Boost-Nesk, and there's a specific reason for this, and it is computational cost. And so essentially, this is the Boost-Nesk equation for groundwater flow. The draw of this equation is that it drops it into quasi 1D. You get to integrate vertically on your hydraulic conductivity, assuming that your flow is predominantly horizontal. And then it's coupled with an ODE that is basically the flow outside the crater rim, and then we aggregate that on the crater lake and update our boundary conditions. Our initial condition is pretty simple. You just fill the saturated zone, crater lake's empty. And these boundary conditions we're going to talk a lot about because this becomes the crux of the problem. What we're doing here is a no flow, and this would apply for the largest craters, the Hellas-sized craters, because essentially your domain would wrap over top of itself, and the entire global hydraulic head would drop. On this side, what we're doing is setting at 0, we calculate a flux across at each time step, and then we add that volume of water to our lake, update the boundary condition, and then proceed with the next time step. And so obviously there's a ton of underlying assumptions here. First of all, we're approximating the crater rim with a vertical interface. On first order, it's probably appropriate, seeing as the 60 angle degree of repose, or 60-degree angle of repose initially, and then it changes when it erodes back. Flow is predominantly horizontal. I'm not sure that's possibly true either. When you create these the accommodation space, and there is a significant portion of flow that's vertical. Are boundary conditions appropriate? Precipitation is hard because Mars paleoclimate isn't constrained at all. And it's actually one of the probably the question for Mars right now is whether you had a wet and warm Mars or a cold, dry Mars. But even wet and warm, it was a ephemeral seas, ephemeral precipitation. And I'd argue that your predominant means for transporting water would be groundwater. Another assumption is that flow from beneath is negligible. We will look at that later with some more multi-phase flow modeling. And that you create porosity as you create the peak ring structure, and that water is basically balanced out by the stuff that comes in the terrace zone. And lastly, it's a big one, is the cold crater floor, that you don't have much melt-water interaction, and you're not losing water out of the system as it interacts with the melt sheet. And so, what we did is we created our model, and we ran it, and this has it's been non-dimensionalized, but this is the first go. And there's going to be a fill versus time plot that comes up right here. I'd like you to pay attention to. You're at 1.5, at 10% of your time steps. And look at how full you are already. And then this speeds up because otherwise we'd be here for a while. But obviously the dynamics of this, we talk about time a lot. Like when do these things fill, and how dynamic is the filling? The majority of the fill, if this model is correct, happen early. And so that's significant. It has implications for later. And so what we did is I worked with a guy named Mohammed Afzal. He works at the Odin Institute, and he's another one of Mark Hess's students. And we put together a multi-phase flow model of the same problem with the same boundary conditions. His model sped up a little bit faster than mine, but qualitatively they're the same. The red would be fully saturated. The blue would be unsaturated. And for those that don't do multi-phase flow, you treat both the air and the water as fluids, and then you model, and you have to resolve both. And the problem with that is the viscosity difference is so great that your time step drops significantly to be able to model that interface. And I believe this model took 6 hours on his computer. So it becomes a tractability issue quick, but we can check this out. And so if we were good modelers, we would just compare these two models and say that, oh, they're quantitatively similar by this degree. And we'd move on, and I'd publish a paper telling you about how long things take to fill on Mars. But we went a different route and decided we would compare it to laboratory data. So in the laboratory, I set up a bead pack cell, which is basically just a cell. It's plexiglass that has enough depth that you don't get interference from the walls. You put a bead pack inside of it, and the varying size of the beads will control your hydraulic conductivity. So the blue part would be filled with beads and water and saturated. In the middle, between the yellow and the blue, I built a little gate system. The mesh part of the gate holds back the beads, and there's actually a full partition that can be removed that would simulate the instantaneous formation of that crater lake. And so you have your crater lake that would be filled here, your saturated media here, with your gate system in the middle. So this is zoomed in and sped up ×2, but this is a shot of our initial results. There's a lot of heterogeneity there due to capillary fringe. But we can already see that it's not at all the same, not at all qualitatively the same or quantitatively. Some of these heterogeneities go away. So there's something to be said about scaling. I don't believe on Mars, over 1,000 kilometers, capillary issue is going to matter at all. But we do see something develop here that we didn't predict, and that's right here. We can see, I think, there we go. And that's the model versus the actual experimental data. And you can see the difference in the shape, and you can see the difference in that interface right there. And so we went and looked at it, quantitatively, and this the circles mark your actual lake level. The blue would be the numeric approximation that we did with that boundary condition where we set it right at the edge of the lake, and then the red would be the experimental data. Obviously, not a good fit at 12 seconds for 13, but it is interesting that later on, towards the end, it actually does line up better, which tells us that this effect doesn't really affect the overall fill time. It has more of an effect on how fast the rate of change, the rate of fill of these craters. And we probably should have expected this. However, we didn't. It's all over the literature. It's something called a seepage face. And on the left there, engineers are really concerned with this in earthen dams and failure of things like that. We reproduced it on the right with varying flows. More flow creates a higher seepage face. Intuitively, we all know what this is. We've been to creeks or creek bed where up on the walls of the creek, the water's coming in and there's a wet margin that's several feet. We've seen this in the real world. And so we took a different approach for how we would address that boundary condition. And what we did is potentials, essentially. We calculated the potential that would be coming out of the saturated water table beneath the lake surface and the one that would be coming out above. And then we added them, calculated a flux, and then reset our boundary condition each time step. And at first, it kind of gives us the results we want until it doesn't. And right there, the model breaks, and there's no feedback right there, and that's why it breaks. It's essentially trying to push water back from the lake into the saturated water table. In reality, you can watch it in the lab. You can affect the seepage face height by the rate you can draw water off that table. So there is some physics involved in how the water table communicates with that lake level. And so we thought, this is the transient problem is much harder than the steady state problem. And so understanding this boundary condition obviously seems to be paramount in understanding this problem. And so what we did is we started setting up some steady state flow in the tank that we have in the lab. We just let flow come in on the left-hand side and drain out freely on the right-hand side under varying rates. All these are under the same bead size at this point, so we can just compare apples to apples at this point. And then what we did is I'd run it for, anywhere from 10 to 5 times and get a flow rate per liter, and then aggregated that. And here I just plotted this just so you can see that the variance in the data is very small. The tailing on the end on the left is actually due to a pump issues. And one of the reasons I wanted to come here too is to see if anybody, they have tanks out here. If anybody had a pump we could borrow until we get the proper hosing for our peristaltic pump. But anyway, and what we did is we aggregated all these, and these all have like N5 to N7 over varying rates. And they all make a nice little family of plots. Interesting thing to see up here is that's the bead surface interface. And we have some concern over whether or not that bead surface interface and the effective length of your domain might actually affect the seepage face heights you see at this side. And there's some interesting findings on that in a little bit. I'm probably running a little fast. So we looked, the solutions for this all over the literature, and some of them are empirical. We really haven't a physics solution of it yet. There's these guys named Rushton and Young. They actually did quite a few papers on this. They compared this also to, I believe, a 2D version with, I forget, they have a slew of papers off this one idea. But most of them come up with a linear solution to this, which is interesting because then once you plot the data we had from the lab, they all are pretty much linearly. And the one I showed you that was the initial one with the spread in the data is this data point down here. The missing gap here is essentially because it's so hard to keep our pump working at those low rates. And so we're waiting on the pump to fill those in. But once so they give a solution that height of the seepage face is down here. It's some scalar. They give you a flux rate. This is a flux across this bound. Hydraulic conductivity in the X direction. And this is a ratio of vertical to horizontal conductivities or hydraulic conductivities, but ours are equal, so that's 1. And then when you multiply it all out, 1.87 times 1, that would be our flow rate. That's our conductivity. You get 14.3. It's definitely not 4.4. So it's interesting that that doesn't quite pan out. And we found other papers where it's similarly off. And so in the meanwhile, while we're looking for a pump, we decided to see if maybe it's the Buzanec approximation that wasn't appropriate for this problem. And so what we did is we just integrated it twice, and we have a data set that has, it out pops the flow rate in, and then also a seepage face height over here as 2 constants. And then we plotted what we got as experimental data versus this analytic solution, and they line up amazingly well, which is fantastic and suggests that we are appropriate in our, at least definitely for this steady state, we're appropriate. And then the other interesting part of this all is when we talked about that the bead interface, is that these solutions just fall right on the beads and then go right down onto their analytic solution, which I think is, I haven't put too much thought on. I think it's really interesting that there's no dependence on the domain there. I'm sure there's some minimal dependence on domain, but it's interesting that you don't have to account for bead height later. I'm going to try to bring us back a little bit to the main idea, and it's that we want to know how these multiple impacts affect the times we can aggregate in elevated geotherms, where we can aggregate the chin-opposite materials we need. We had this earlier, that permeability field we made, and you're flowing left to right, and you have that yellow highlighted field where a particle, something, biomass. I don't get into really what the whole idea of what is a significant time, biologically significant time more is the point we're at. I'm not sure that's constrained as to what is biologically significant, but statistically speaking, just Urey Miller type experiments where you have organic compounds and you put the energy in it, the more time you have to actually react, the more time in elevated geotherm, more time with more energy and more element cycling, the better. That's my rationale behind this. And so say you're some piece of biomass floating from left to right in that field, you might make it in this guy, or you might be coming out. But once you alter that field, you're definitely going in here. And the Chicxulub system, I think it still has an elevated geotherm, and no one really knows how long these systems are lasting. I think some of the geochron stuff now is 8 to 12 times what the models predict for the longevity of these post-impact hydrothermal systems. And so can you aggregate that time is the question. Because now, you're going left to right, you hit this crater, and now you're bouncing up gradient again. And this is all on the way to dichotomy at some point. And the question is, what does it take to move this stuff? What are the time periods that it takes to move there? Because if there's a significant difference between flooding a system and slowly dripping water into a system. It's also a significant difference. I'm sure there's some type of sweet spot to where if I need to get up out of that localized sink, if I'm sitting in here, what is the gradient required to even pull it up and out or get it into here? Because it's obvious that the hydraulic head will communicate between craters. What is not obvious is what you need to communicate material. What does it take to get material up and out of one sink into another? My intuition is it takes more than one impact, but maybe one to get you up and out and another to move you somewhere else. But that literally cannot be answered until we get a grasp on this, just the single crater fill time. And the overall implications of this is this cohabitability idea that I really like. Natalie Cabral, she led SETI for a long time. She's somewhat prolific. People probably know her, but she has the idea that planets and life co-evolve together. And like on Earth, this makes sense that, as the stromatolites produced oxygen, they oxidize the oceans, you have the banded iron formations. Life literally, terrestrial erosion rates changed due to it. And so life literally altered Earth. Well, on Mars, you lost your dynamo, your magnetic field dropped, your atmosphere eventually was stripped away from, solar wind, and plus Mars is only a third the size of Earth, so it has a hard time holding its atmosphere anyway. So now you're having a hard time, forming liquid water on the surface, and the pressure isn't high enough. You definitely don't. There's a young sun problem. You don't have enough energy. So where could life go? Where could life evolve as a planet evolving and the planet's essentially dying? And that would be underground. I don't really agree with most of these arrows, but you can see how Hellas here is its own basin, and how anything along the way to that basin would be fair game to stop off at. And anything, Azure has its own basin. We talked about Tharsis just a little bit. I mean, Tharsis is an enormous feature on Mars that would actually have implications. Mars has obliquity cycles that are much larger than Earth's because its moons are too small to actually, constrain the obliquity shifts. So you have all these large scale gradients that are driving water across Mars. And the question is, how long does this take? And is it significant enough time to keep these things in elevated geotherm? And so to conclude, the development of seepage phase should have been expected, and we didn't see it coming, but it's there. And does it scale is a question. And we need to parameterize that boundary condition. And that's the key to lining up at least the laboratory data with our model. A steady state solution of the seepage phase is needed before a transient can be obtained, and the boundary condition can be parameterized. There's some interesting ideas we have, and I think it'll probably be on another talk about it being a problem with energy, to where you can. Why do these seepage phases choose the shape they choose? I mean, you have one set of flow coming in one side, and you have a height on the other, and it could choose any shape in between at once, but why does it choose a specific one it does? Dr. Hess has an idea that it's energy minimization, that, as you shrink the seepage face, the velocity of the fluid has to go up, which requires a certain amount of energy. If you make it higher, then there's a certain amount of energy required to counteract gravity. And so maybe there's some minimization function that can be done. And I like that idea a lot more than just using some of these empirical solutions, because I feel like the empirical solutions have Earth physics baked into them. Whether it matters enough in the first order estimates we're doing, that's yet to be seen. And the seepage face is relevant to the habitability assessment of PIH systems because it may act as a constraint to fill time and allow for more interaction and sustained periods of elevated geotherm. And moreover, Mars has, there's debate as to why Mars even had running water with the young sun paradox. You had 75% solar influx. It's not big enough to hold enough atmosphere to keep it warm enough. So why did it really have flowing water? And in thinking about this, if you trickle water into melt sheets, you produce much more steam than when you quench a melt sheet. And similar to like a pan on your stove. If you drip water on it, you produce a lot of steam. If I dunk it in the sink, it goes out. And I know no Martian climate models look at any type of steam production from these systems. And so future work, we want to keep adding to our data set with, once I get the pump with sufficient accuracy, I can trust it. We're going to properly parameterize our boundary condition at the crater rim, and hopefully we can extend the 1D pretty soon so we can get some fill time estimates for some terrestrial analogs. And long-term we'll be removing all of those simplifying assumptions. I'm not sure whether the next step is that or whether seeing what we can do with multiple systems forming and seeing if we can come up with some scaling laws for that would be appropriate, but that would be probably in a year or two. And then the 2D implementation of the Boost-Nesk. And that's the entire goal of this, is we really want to stay within that Boost-Nesk approximation. You can't really do it in 3 dimension with any other form. I mean, it's that that quasi 1D nature of doing it 2D here, which makes it quasi 2D and when you're in 3, that makes this tractable. And the aspirational work is that I actually do want to do some climate modeling on it. And a shameless plug for Dr. Hess's class. We're actually using this problem for his next modeling class next semester. And he's done series before cryovolcanism. I think last year he did ice mechanics on Europa. But this next year will be on the basics of modeling and how to get nitty gritty on the details of numerics using this problem. With that, I'm going to leave my email address. If anybody's watching this online and wants to ask any questions, I love talking about it. I always have to thank my kids because they're more patient with me than I would ever be. And I'll take any questions. That was fast. Apologies.
No worries on the timing. If there's any questions, you can feel free to call them out. Okay, I'll start it off with a question. Can you make any speculation or hypotheses about what you would expect to see if you did remove some of those simplifying assumptions like flow from below or a non-vertical crater rim?
So yeah, we've talked about it. So I think the flow from below, like I don't have any, this is just my intuition. I think that like the flow from below matters initially, obviously, because you have empty pore space and you're making a ton of pore space. But once that fills, I mean, that matters for all sorts of things like the production of steam and how quick you fill and if you lose any of the stuff that you're filling with. But once you fill that space, I don't think it matters as much because I think the restricting variable would be the amount of water you can get to the system. And that's going to be restricted by like porosity at depth away from the crater, if that makes sense. That's my thoughts on that. I think that as the rim recedes, I think you're going to smear out that seepage face more. And so I think it actually, like, this is going to be your limiting like condition essentially. I think that some of those, the listric faulting in the terrace zones is going to speed things up. But then again, you get into like diagenic things that like, I don't think that you can even model on Earth, much less on Mars.
Cool. Other questions?
Yeah, I had one. You think it's possible that, like a comet impact could deliver liquid water and keep it hot enough for, to stay for a while from the impact energy?
I think that that is pretty. Yeah, I think that it wouldn't stay there. I think that you're going to volatilize it, and that's literally like what we're getting at is the energy impact. That water probably comes back in form of precipitation. But yeah, I think that more so we're looking at the stony meteors that produce larger impact structures. But I don't know enough to comment really on like how water was brought. I think that's like really an open discussion. That's not my lane as to whether you had water saturation that was previous to comets or not. I don't know if that answered it or not.
Okay, thanks.
Anyone else? All right. Well, Eric, thank you so much for sharing that with us. That was a really enjoyable discussion hour.